Am I on? Okay. Hi, my name is Brian McClanahan. This summer I've been researching battery prognostics. This is an overview of my presentation. First, I'll define battery prognostics. I'll discuss some criterion of prognostic algorithms. And I'll speak on the objectives of battery prognostics, some of my current work, and my plans to predict remaining useful life of a battery, and I'll explain why that's important when I get to that section, and some questions. This actually isn't the overview of my presentation or my latest presentation, so apparently I have the older one, but I'll try to work with this. And this is my definition of, prognostics. Prognostics is basically an engineering discipline focused on predicting the point in time when a component would no longer function some type of function which it's supposed to. Some criterion of prognostic algorithms include accuracy, which is algorithm's ability to predict what actually happens in comparison to what actually happened. Bias on algorithms' tendency to make predictions that are either too high or too low. Resolution, algorithm's ability to distinguish between different events occurring. And sharpness, the ability of an algorithm to predict extremes. This is a metric used to assess the performance of prognostic algorithms. It's called the alpha lambda index. The diagonal line that you see going across the middle of the plot is the actual remaining useful life left of a battery in cycles left. And the three different sets of dots that you see are three different types of prognostic algorithms. The primary goal is to get more accurate as you make more predictions in your time series predictions. So the red line that you see, the red margin that you see, represents a 15% margin of the actual remaining useful life of the battery. And you see as the algorithms make more and more predictions, they tend to get more and more accurate, except for the green one over here. But basically, the objective is to stay within that margin after a certain point in time, that 15% margin. Some objectives of battery prognostics include predicting the remaining useful life of a battery, how many more discharge and charge cycles it has left. To predict the state of charge, how much longer will you be able to discharge a battery within a certain discharge cycle. And to predict the state of health, which is the rate at which the capacity is faded in comparison to its nominal capacity. One of the characteristics of the capacity fade, one of the strong factors of capacity fade is how long the battery is allowed to rest between discharge cycles. If the battery is allowed to rest longer opposed to shorter, then its capacity will fade less or will actually increase opposed to fading. So on the top here, I have lengths of discharge, the amount of time that a discharge cycle lasts. No, oops, sorry. And on the bottom, I have the length of rest that the battery was subject to in between two consecutive discharge cycles. As you can see, when the battery is subject to a longer period of rest, the capacity has a tendency to increase opposed to decrease, as usual. And what I wanted to do was, I wanted to create an algorithm which would determine the next length of discharge given the amount of time a battery was allowed to rest. And the way I went about doing this is, actually I need to get I can't do it. I actually had a diagram showing you this, but I'll just improvise. So what I did was I created three vectors. And these three vectors were the intervals of rest. Since rest is a continuous value, I had to define intervals for rest. And each interval has a min and a max. And then I have time differences which occurred as a result of a specific interval of rest. So these indexes correspond to each other, of the rest periods and the time difference of these two different vectors. So what I do is I find a certain interval of rest, let's say it's 2,500 seconds to 3,000 seconds, and I find all periods of rest which fit within this interval. And then I find the corresponding time differences of those rests. So let's say I had a rest that fit into the interval right here, and right here. The corresponding time differences to those rests would be in the exact same indexes in this time difference vector. So what I do is I find all of these time differences, and I put these time differences in a vector. Let's call this the time diff vec. And all these time differences in these vectors, what I do is I find the mean of these time differences, and I find the standard deviation of these time differences, and then I use that to create a probability distribution or a probability density function in what I call my density matrix. Now, the peak of these density functions will be the time difference that's most likely to occur given rest within a certain interval. So each of these intervals will have a different probability density function, which corresponds to the lengths of the time differences that occur due to rest, which fall within this interval. If that makes sense. And this shows the values of time differences within certain rest intervals. As you can see, they have a tendency to take on, the bulk of them have a tendency to take on one specific value. So by taking the mean of all these different time differences, I get a value that's close to somewhere in here, which is most likely to be the time difference that will occur if I have a rest within a certain interval. And maybe I didn't explain this histogram as well as I should have, but the bottom is the values of the time differences, and the X represents the quantity of items which took on these values. And these are my results. I got the battery data from NASA Ames Research Center, and it came with 4 batteries, batteries 5, 6, 7, and 18, data for 4 different batteries. And I trained the batteries on battery 5 and 6. That's what I used to create this lookup table of densities. And then I tested the battery on 5 and 6 just to see if it worked. And then I tested it on 7 and 18 as well to see how accurate it was. And in the case of my worst average percent difference between the predicted value and the actual value was 0.501%, and that was when it was tested on battery 18. And the worst prediction was off by 100.37 seconds, and that's also when it was tested on battery 18, which is the battery that it wasn't trained on. And this is a histogram showing my time differences between the predicted value and the actual value for each prediction that I made. The x-axis represents the time in seconds that I was off by, and the y-axis represents the quantity of items which take on these values. A negative value means that I overshot. That means I predicted that the actual time will be longer than what it actually was, and vice versa for the positive side. It's important to establish a relationship between the rest and the time difference of consecutive lengths of discharge, because once I do that, I can take a usage profile and determine the remaining useful life based off of that profile. Say I know that, okay, I can expect this many rest lengths and then that many rest lengths. I know how those rest lengths will affect the capacity. Therefore, I can predict the remaining useful life of the battery. And some of the possible methods that I've been exploring to accomplishing the task of predicting remaining useful life include a good Turing frequency estimation without tears. And I learned about this from a paper that I read, and the papers by William A. Gill and Jeffrey Sampson. And basically what good Turing techniques do is they allow you to estimate the frequency of certain occurrences within a population by taking a sample out of that population and analyzing the frequencies within that sample, and then using the frequencies within that sample to estimate the frequencies within the population at large. So let's say this is my entire population. It consists of A, B, C, D's, E's, F's, G's. Right, let's say all of these are A's. Let's say all of these are B's, E's, F's. Okay, so let's say that I take a sample right here somewhere. Now let's say in this sample I have 2 A's, 2 B's, and 2 C's. So it's 33% of each. But what I didn't get any D's, I didn't get any E's, and I didn't get any F's. So the key idea of a good Turing frequency estimator is it allows you to account for the items which you didn't get in your sample, which enables you to better estimate the true proportions of the population. And this will be useful for analyzing the usage profile because I can see certain lengths of rest or certain patterns of rest and then use those to determine my remaining useful life. But I also have to account for certain patterns which I have not seen as of yet. And I also want to explore using a particle filter, which is basically just time series predictions based on Bayesian inference. And my rough plan to estimate the remaining useful life using the particle filter, which is an idea that isn't novel, but it's something I want to implement to get a better idea of how prognostic algorithms work, is to propagate and innovate particles which are states. And these states would represent the capacity and the rate of capacity fade. And what I mean by innovate is you take random samples, right, which are coming from some probability distribution. And you use these samples to predict what you think will happen. And then you look at what actually happened and you weight the particles accordingly. The closer particles will get heavier weights than the particles that were further away from what actually happened. And the idea is the particles should evolve over time to be true representations of the probability distribution of the state. And that probability distribution can be used to estimate the remaining useful life of the battery. And my idea for RUL prediction using a good Turing method, I basically just explained that. What I'll do is I'll take a sample of rest lengths, which the battery has been subject to already, and then I'll look at the proportions of the different frequencies of rest lengths, basically the different patterns of rest lengths the battery has been subject to, and I'll extrapolate that information to try to figure out what type of rest the battery will be subject to in the future. Mind you, rest length is only one of the factors that determines the remaining useful life. It's also factors such as temperature and other things about the impedance of the battery that determine the capacity fade. But with the NASA battery data set, they have a very controlled experiment. Like the temperature is constant, direct current is applied to it, so impedance isn't really much of a factor. So I'm trying to work with the information I have now and then build on that later. But for the time being, basically, I'm looking at rest inference as my predominant factor. And then I'll sample these different rest lengths from the battery's usage, and I'll try to extrapolate that to predict how the battery will be rested in the future. And I'll also account for how the battery hasn't been rested. And I'll use how the battery hasn't been rested to model the uncertainty of my algorithm. And these are my references. Are there any questions?
You said your error was only 0.5%?
0.5 or 1%.
Okay.
But see, the thing is that
How did you compute that?
Okay, how I compute that is, right?
I think the end of discharge time is about 2,000 to 3,000 seconds, right? And his prediction can be only off by, what, a maximum of 100 seconds.
Right.
But on average...
Right, but based on how much of the...
Yeah.
Okay.
I don't understand exactly what you're predicting from that. If you go back to your curve, the plot,
right,
with that one. Okay, how much of that data are you using?
I use all of it. What I do is I'll take this point, right, and I'll say, okay, this is my previous discharge, and then I'll look at the rest period that happens immediately after this discharge, and given this length of discharge and this rest period, I'll predict the next length of discharge.
Okay.
And I do that for all of them.
Okay.
Any more questions?
I'm curious about what you were saying about impedance of the battery. You discounted because of why?
Because they were subject to direct current, right?
DC.
There's different types of impedance. You have Warburg impedance, which is due to diffusion processes between the electrode and the electrolytes.
Okay.
And then you also have charge transfer impedance. Now that is a factor actually. Charge transfer impedance deals with the chemistry of the battery. Like if you have more products than reactants, then obviously you aren't going to get a good transfer of charge. Yeah. Right? Now that is a factor in this case. But Warburg impedance, what happens is Warburg impedance, it deals with diffusion processes, right?
Okay. Electron or chemical diffusions?
Yeah, them chemical fusions. And not chemical fusions, basically current diffusion through the electrode, from the electrolyte to the electrode. And so what happens is it's only It's only really an impedance when alternating a current is applied to the battery.
Okay.
But alternating current isn't applied to the battery.
Okay.
So of course, if an alternating current is applied to the battery, you know, R times I is voltage, right? So it increases. But since R isn't a factor, it doesn't affect the voltage of the battery.
Okay. So you pretty much just did like a lump circuit model and just said that's one large resistor, and you said that one's 0 and this one's this value.
Exactly.
This one's this value. And you took any like charge distributions and model as like a capacitor. And because it's DC, you have to count it depending on it's a DC block, so it'll be an open circuit.
Right. Yes.
Was this evaluated before? Were other methods applied to predict this? Because it still seems like it's very good. Your results are really good.
Well, that's only predicting the end of discharge time, assuming that the battery is applied to a constant current load.
Right. The ambient features of like the actual use of the battery would make that much more hard to implement.
And that's what NASA wants.
No, that's just for some practical usage. You can test if you predict the battery usage, like the laptop. If you keep doing that, you can see the remaining capacity. But I think the most challenging part is to predict how many times you can be using this battery, rechargeable battery, for similar operations. And that's like the RUL prediction. And what he did on the data set is like some aging process when the battery was repeatedly charged and discharged until it's no longer usable. And at the very beginning, you can predict how many times you can use that battery. And that's very useful.
Any other questions? Thank you.